Hi, welcome everyone to our next session, class 12 mathematics, and we start with a chapter on matrices. Firstly, an introduction on matrix. What is a matrix? A matrix is a rectangular array or arrangement of numbers, symbols, expressions, etc. arranged in rows and columns. So what do you mean by this? It is a collection of a number of elements which are arranged either horizontally or vertically. The horizontal arrangement is called the rows and the vertical arrangement is called the column. The order of a matrix is the number of rows into the number of columns. Here, as you can see, the ones highlighted with red is a row, and the order of this row is 2, and the order of the number of columns present there is 2. So the order of the given matrix is 2 into 2. We come to the basic types of different types of matrices. The first one is the identity matrix. In the identity matrix, you have the diagonal elements, that means the ones which are along the middle, the diagonal. These are unit 1 and all of the elements will be 0. Coming to the next one, the null matrix, which has all elements equal to 0. The row matrix is the one which has only rows, and the column matrix is the one which has only columns. And a non-singular matrix will be a matrix whose determinant will not be equal to 0. Moving on to the operations on matrices. We have 4 kind of operations on matrices. Firstly comes the addition and the subtractions. The examples are shown there. For addition and subtraction, it's important to keep in mind that the order of the two matrices which you are adding or subtracting should be the same. Coming to the third operation is multiplication of a matrix by a scalar value. When you are multiplying a matrix by a scalar value, you are multiplying each element of the matrix with the same value. Here I have written 2a. 2 is getting multiplied with 2, 3, 4 and minus 1. Each of the elements is getting multiplied by the element 2. Moving on, we have the multiplication of two matrices. For this, it is very important to know that the number of columns of your first matrix should be equal to the number of rows in the number of columns of your first matrix should be equal to the rows in the second matrix. In such a case, the two matrices are said to be compatible for multiplication. If the columns of the first matrix is not the same as the number of rows in the second matrix, then the two matrices will not be compatible for multiplication. I have given the example there. When we are multiplying this row with this column, keep that in mind. It is the first row and the first column. 1 2s are plus 2 1s are plus 3 into minus 1, which I have written it down here. Next we come the first row and the second column. It is 1 1s are 2 into 0 and 3 into 3. First row, second column comes to this position. Moving on to the third one, first row, third column. 1 3. First row, third column. This is the position for the first row, third column multiplication. 1 1s are, 2 1s are, 3 into minus 2. Moving over to the next row, we have second row, first column. I have it here. Second row, second column. 2 2. This is the position 2 2. Second row, third column. This is the position for 2 3. Please keep that in mind, that it is always the row of the first matrix which is giving me the first position and the column of the second matrix. The row position of the first matrix, the column position of the second matrix give me the position where I am going to place my answer. See here, the order of this matrix was 2 into 3. The order of this matrix was 3 into 3. You see here the number of columns of the first matrix and the number of rows of the second matrix was same. That is why we could multiply the two matrices A and B and see the resultant here. The order of the resultant matrix is the number of rows in the first matrix and the number of columns in the second matrix. Moving over to, we have the transpose of a matrix. Transpose of a matrix is as simple as just interchanging the rows and the columns. That means the ones which were the rows in your original matrix now become the column in your matrix, and the ones which were columns in your original matrix now become the rows. You see here 1 3 2 5. The row was 1 3, the second row was 2 5. Here the first column becomes 1 3 and the second column becomes 2 5. The row here becomes the column here. Same holds for this one. The row here becomes the column here. Coming to the adjoint of a matrix, a very important topic for class 12. If we have to find the adjoint, what we do here is we find the cofactors along with the signs. We have 1 here. When we are going to find the cofactor of 1 1, we leave out this one. The resultant portion left, this 0 1 6 minus 1, we get the matrix here. 1 coefficient of 1 comma 2 1 comma 2 is 1 comma 2. The cofactor of this will be leaving out this column and this row. You are left with 4 0 6 and minus 1. The cofactor of 2 comma 1, sorry, the cofactor of A21 means the leaving out the element of the second row and the first column. That means you leave out this element. That means you leave out this column, you leave out this row. What are you left with? You are left with minus 1 2 1 minus 1. The cofactor of A22 is this element. You leave out this element. That means you leave out the second row, you leave out the second column. You are left with 1 0 2 and minus 1. The cofactor of 3 1 means leaving out this element. That means you leave out the third row and the first column. So you are left with minus 1 0 2 6. The cofactor of A32 means leaving out this element. That means you leave out this row, you leave out this column. You are left with 1 4 2 6. Similarly, you have the cofactors of A13, A23 and A33. When you are setting up the element, you take the transpose of them and it becomes, if you match it up with the elements in the previous page, you get these elements, and these elements when taken the transpose, you get minus 6 4 4. This row becomes a column here and this row becomes a column here. Coming over to the inverse of a matrix, the inverse of a matrix is given as adjoint of A divided by the determinant of A. I have given an example here. You have a matrix A here. First, we find out the determinant of A. It's necessary for you to check if the determinant of A is 0 or not. In case if it is 0, then the matrix becomes a singular matrix, and then the inverse doesn't exist. Here we have the determinant A as 1 into this portion. That means the cofactor of 1 minus 5, the cofactor of 5 plus 2, the cofactor of 2. The resultant value we get it as 1. This is not equal to 0, hence the A inverse exists. Now adjoint A, I have taken it out in a way similar as shown in the previous example. So A inverse is adjoint of A into 1 by determinant of A. Moving over to, we have the next portion as symmetric and skew symmetric matrix. When we are taking the transpose of a matrix, if the transpose is the same as a given matrix, this matrix is symmetric. Here A transpose is equal to A, then the A is symmetric. And if A transpose is equal to minus A, then A becomes a skew symmetric matrix. Two examples are given here. If you see here, the rows here are becoming the columns here. these two matrices are exactly the same. So B transpose is equal to B. Hence, B is a symmetric matrix. We have another example here. We have taken A as this. When we are interchanging the rows and the columns, here A transpose element wise is the same as A, except that it has the signs are opposite to what A had. That is why A transpose is equal to minus A. Hence, A becomes a skew symmetric matrix. A common use of symmetric and skew symmetric matrices is that you have to express a given matrix as a sum of a symmetric and a skew symmetric matrix. We are given with a matrix A 3, 1, 5, minus 1, and we are taking out the A transpose 3, 5, 1, minus 1. The rows becomes the columns become the rows. We are finding out two matrices P, which is half of A plus A transpose. We have done the addition here, and then we have done the scalar multiplication of each element of the addition part multiplied by half. It is the scalar multiplication of this matrix with half. Each of the element is getting multiplied by half. We get this resultant matrix. Matrix Q is half A minus A transpose. If we do the subtraction, we get this, and then it is scalar multiplication with half, you get this resultant. Now we see that if we take the P transpose of matrix P is the same as P, so P is a symmetric matrix. If we take the transpose of Q, Q is a skew symmetric matrix. Hence, if we see this now, P plus Q becomes half of A plus A transpose plus half of A minus A transpose. If you take the sum of this, solving it algebraically, you get A. Hence, we could express A as the sum of two matrices, A, P and Q, where P was a symmetric matrix and Q was a skew symmetric matrix. Moving over to the uses of matrix part, we will be solving a matrix using, we will be solving a system of linear equations using matrix. We have been given three linear equations in three variables A, B and C. Now these equations, we are going to write it in the matrix form as AX, A into X equal to B, where A is my coefficient of A, B and C. My B matrix is the resultant answers, and my X matrix is my unknown, the variables A, B and C. Firstly, we check if determinant of A is equal to 0 or not. Had it been equal to 0, then we would have opted for other methods. But since it is not equal to 0, it's a non-singular matrix, hence A inverse exists. Adjoint A, the way we had taken out in previous examples, is taken out in the same way. So we get A inverse as this. Now X is equal to A inverse B. This is the formula for it. So A inverse, I've got this part and B was this. If we multiply minus 12 into 9, that's minus 108, plus 2 into 52 plus 2 into 0. 16 into 9, minus 3 into 52, minus 5 into 0, minus 8 into 9, 1 into 52, 3 into 0. Algebraical addition and subtraction of this and then division by minus 1 by 4 gives you this. Now my X was A, B and C, a column matrix. So A takes the value of 1, B takes the value of 3, C takes the value of 5. Moving over to the elementary transformations. Now, elementary transformations of a matrix is this, the row and the column operations. When we are finding the inverse of a matrix by elementary transformation, we generally opt for row transformations because row transformations are much easier to be handled. And it is suggested that you opt for row transformation because Many a times it's given in the question itself that you have to use the row transformation. We have been given a matrix 3, 0, 2, 2, 0, minus 2, 0, 1, 1, and we have to find the inverse of this using the elementary transformation. We write this matrix in the augmented form. That is, we write the given matrix here with a dotted line in between and the identity matrix on the right hand side. Our main aim is to change our given matrix A into the identity matrix, which in turn will lead to certain transformations in I, and the resultant part that we will be getting after getting an identity matrix here, the resultant part that we will be getting here will be my A inverse. Firstly, I try it as R1 is equal to R1 plus R2. We are going to add up the first two rows, and the resultant we are going to write it in the first row. We get this. The other two rows, R2 and R3, are unturned. Then we opt for my main aim was to make this as 1. So that is why I divided it by R1. I divided R1 by 5. So this becomes 1, 0, 0. Other things are still untouched. Now I've got my first initial point 1. My next motive is to make this as 1. For that we start with R2 will be R2 minus 2R1. My first and the last rows are untouched. This row changes. Next I have it as R2 is equal to minus half into R2 to make this as 1. These two rows are unchanged. This row transforms. Next I interchange R2 and R3. It's interchanged. See here, 0, 1, 1, and the last row was 0, 1. The second row was 0, 0, 1, and the third row was 0, 1, 1. Here after the interchange it becomes 0, 1, 1, and R3 becomes 0, 0, 1. You see here, my second motive is attained. These two are zeros, these two are zeros. My only aim is to remove this one now. For that I do R2 is R2 minus R3. That gives me a 0 here. You see, my resultant matrix here is an identity matrix. And then I have got certain changed elements here. Initially, we started with an identity matrix on this side and a matrix A on this side. When we are doing all these transformations, that is leading to an identity matrix on my left hand side, and the resultant matrix that we have got on my right hand side, that becomes my A inverse. If you want to check whether this is the real A inverse or not, you multiply A into A inverse. The resultant of it should be an identity matrix. With that, we cover the main portions of matrix. Hope it is useful for you, and do give me a feedback. Thank you.